Let's code a globe that's actually 3D, not just a 2D image wrapped around a sphere, to find out if modern web browsers can handle the kind of VFX I want for my game dev project. So, we're going to make a point cloud with 1.2 million pixels using the WebGPU renderer from Three.js with React 3 Fiber to see if we can animate each point with a TSL shader while keeping it fast to load and smooth to run on a smartphone. We'll start off by covering how the globe works, and then we'll get right into gathering high-quality geographic data to process in Python. As you can see, the geography is highly detailed, with coastlines, lakes, and rivers at high resolution. The elevation is exaggerated because in real life, our planet actually looks quite smooth from a distance. With the sliders, you can adjust the amount of exaggeration, turn the spin and particle animations on or off, and change the colors as well. For that, I have 4 presets, and you can blend between the land and water color based on elevation, set the opacity of the sphere, and tweak the amount of glow and lighting. The threshold sets how bright the land has to be in order to be affected by the glow, and the lighting simulates a sun that rises in the Pacific near Japan and sets in the west as you make your way across the Atlantic towards the Americas. Now, that's a lot of features, and by the end of this video, you're going to know exactly how to build each one. I've also linked to the globe in the description in case you want to check it out as you follow along. Here's how to make the globe. First, we need to get geographic data, but for our needs, you can't just npm install D3 and use the map projections it comes with, or find an image off of Google to wrap around a flat sphere, because we're going to combine 2 different types of data, shape and elevation, into a single dataset. For shape data, go to naturalearthdata.com and click download. Here you can get the shape files for the physical features of the planet, but if you look closely, you'll also see that they have country borders in addition to raster files containing elevation. Why not just use that? Well, let me show you. Here you can see that the file size is a couple hundred megabytes. This data is already downsampled, and you would have to downsample it further to make sure that it loads quickly on a website. So instead of downsampling already downsampled data and trying to force it to look right, we're just going to get the raw data and downsample it ourselves. That way, we only have to downsample once. For elevation data, visit the website for the National Centers for Environmental Information at ncei.noaa.gov. Then under Products, click Search/Filter and type in eTopo, E-T-O-P-O. Then click on the Global Relief Model and scroll down. We have a few options here. The most detailed dataset is the 15 arcsecond resolution, but for me that was a little bit too large, so I used 30, and I downloaded the ice surface elevation geotiff. Click on the link to download it. So we have a few gigabytes of data, and our challenge now is to get rid of anything we don't need. The basic idea is this. We take the shapes of all the land, cut out the bodies of water, and add elevation to the parts that remain. What about the oceans? Our data includes bathymetry or ocean depth, but I wasn't happy with how it looks, so I decided not to use it. To process our data, we're going to use Python because it has a more mature geospatial ecosystem. A lot of people have spent time optimizing the libraries we're going to use. They actually run in C, and they're very fast. You can use a full-featured IDE, like PyCharm's Community Edition, which is free, to set up your environment and install your dependencies. Create a requirements.txt file and add GeoPandas, NumPy, Pandas, and raster.io to it. Then, create a script file and install your dependencies when the IDE prompts you. Open the elevation and shape data that we downloaded earlier using raster.io and GeoPandas. Normalize the shape files, subtract the bodies of water, rasterize the shape that remains into a landmask, then create an old-fashioned loop to sample the elevation points for areas within our landmask. A couple tricks that I used to get a good result were to make the rivers 6,000 meters wide so that they're actually visible in our point cloud, and to sample elevation points for the rivers directly. And then we save the result as JSON. The script can take some time to run, so while you're making changes, I recommend using lower resolution data, and once you're happy, you can use the highest detail files. If you would like my version of the script, you can get it from my Patreon. Let's move on to Three.js, where we'll build and optimize the 3D model before handling lighting and animation. Create a new React project by opening your terminal and typing in npm create vite at latest. Then choose TypeScript with the React compiler. We'll add our Three.js and React 3 Fiber dependencies to our package.json file, and now we're ready to go. Create a sphere that's slightly smaller than the radius you set, so that there's no overlap with the point cloud at sea level. Then import the JSON file we created in Python, which is 75.5 megabytes, but we'll take care of that later. Then we'll convert our latitude and longitude data points into spherical unit directions, which will scale by elevation, which is also scaled. Our point cloud needs a geometry and a material. For the geometry, we'll use the functions defined earlier to set up attributes for direction, elevation, land, which is 1 for land and 0 for rivers, and an empty attribute for the final position of each point. We'll use these to help define the material. Each point's color is defined by its elevation and the blend slider. I'm using Leva to create the control knobs, and Zustan to share those values with the 3D components. Add orbit controls to make it look like our planet is spinning, and now we have version 1 of our globe. But as mentioned earlier, it's quite a large file. So we're going to make 2 key optimizations. The first is to respect people's bandwidth and reduce the file size, and the second is to respect people's battery life. Instead of loading a large JSON file and building the globe at runtime, we're going to save the full globe as an efficient binary so that we only have to download the exact data that we're using. Now we can import the GLB file and remove the code for setting up the geometry, which we no longer need. Note that our sphere and point cloud are 2 separate nodes within the file, and your attributes will be prefixed by underscores. To avoid wasting battery power, we're going to set our canvas frame loop setting to demand instead of always. Now, instead of rendering 60 times per second, our scene will only re-render if we call the R3F invalidate function, and we'll set this to be called only when we change our sliders or when the globe should be animating. Our scene has 3 lights, an ambient light and 2 directional lights. The ambient light serves to illuminate the whole scene, but the intensity is muted. The first directional light acts as a rim light, lighting the globe from the side to simulate a sun, and the second one acts as a backlight placed at the bottom slightly behind the globe. For these two, both the color and the intensity can be adjusted with the sliders. It's important to note here that the globe is actually stationary, it's not spinning, and the orbit controls camera moves around the globe to simulate the planet's rotation, so the rim light is also stationary next to the globe, but the backlight is parented to the camera and moves with it. For the glow effect, we're going to wrap our entire 3D scene with a post-processing component. The idea is to take the render output of our scene, pass it to a glow or bloom filter, and combine them. For animating our particles, we're going to add 3 sections to the material of our point cloud, 1 for animated position, 1 for the motion delay or blur effect, and 1 for fading out the particles. Each particle moves towards its target elevation from slightly below, and regardless of distance covered, the travel time is constant. You can experiment with a constant speed as well. At this point, all the variables are up to you, because it's based on what you think looks good. And then I add some randomization across 2 factors. One is the timing, so that the particles start and end their animations at different times, and the second is along the path. Instead of traveling in a straight line, they wobble. For the motion delay, we take the inverse of the camera motion and clamp it along the primary axis of movement. The length of the inverse camera motion path is determined by elevation, with low elevations having a small path and higher elevations having a longer one. Additionally, I add some randomization to the path lengths. This effect was the most useful for me because I can use it for secondary motion in the animation of my game characters for things like clothing and hair, and for animating leaves and grass in the environment as well. For fading the particles out, I apply a mask from a certain elevation threshold and apply some smoothing so that it's not abrupt. As mentioned earlier, you can check out a demo of the globe by following the link in the description or get the source code on Patreon, but I encourage you to experiment with both the shader and the data. Natural Earth includes forest and desert data, which you can add to your own version of the globe. Now the data isn't perfect, just look at the Himalayas or Antarctica, but let me know in the comments if you create something interesting. Subscribe for more videos on the art and code of game development, and I'll see you next time.